of lectures, hackathon, competition, and the amount of code you've written in the past few days. You worked really hard in the last 2 days about different use cases. So we have 16 teams and 16 use cases, all different. Today you're going to give your presentations. So we did split the 16 teams into 2 groups of 8 teams, and each group will have a different jury. And the best 2 teams from each jury will be said to be the winning teams. The use cases you've been working on for the past 2 days or so were a combination of use cases brought by the industry and internal use cases brought by Quantinuum. And those are, I would say, much more complex in nature than use cases you could have found 2 or 3 years ago. And it's a testimony of how the whole industry or the whole field kind of evolved in this past few days. So first of all, thank you very much for being part of that. It's not a trivial effort by far, so I recognize that when I saw all the different teams in different rooms, you were working hard, and those are not easy problems. If the problems you were tackling in 2 days could be solved in 2 days, people would know it, and the industry would be totally different. But this is only the beginning. You've been working in the past 2 days with a team, maybe going to collaborate again and continue working with the teams. And maybe the mentors, either the mentors from Quantinuum or the mentors from the industrial companies. And I actually strongly encourage all the different companies that came to the hackathon to re-invite again the participants internally to give internally the presentations to keep a momentum after the hackathon. Because we don't want a hackathon, we don't want the whole quantum effort to stop tonight. We want to have a momentum and continue because we're building together something that is not only for this week, but for the next years or decades to come. So you will be given your presentations this morning until around 12-ish. So every single team is going to give a presentation of 10 minutes plus 5 minutes of questions and answers. As I told you on Friday morning, Friday morning, you will be judged by both the jury members and the mentors. So the ratio of the marks is like 2/3 for the jury and 1/3 from your mentors. And after we're done with the presentation, we'll reconvene this afternoon in a exceptional venue in central Trieste called La Sala Piccola Fenice. We'll have shuttles bringing you from the ICTP to there. And we'll have a welcome speech from the director of the ICTP and the founder of Quantinuum, and we'll be giving all the awards, and we'll have a fun cocktail time, and you'll be able to network with the people from the different companies, people from Quantinuum, and you'll be able to relax after this intense week, and I know what this is. So on this short introduction, I will let Thomas re-indicate again the splitting of the 2 teams, say the team names assigned to the 2 juries, and he'll be the master of the ceremony. So Thomas, please go ahead. We did all the food for 140 people, so you better eat.
It's going to be very quick. I'm just going to say which team will move to the second room, Aula Stasi, on the first floor. And can you hear me? No. Further away. Okay, perfect. And which teams will stay here. So in the team that will leave, our team number 2, Air Jordan Wigner. The team number 3, with no name, I don't know. Team number 6, Eni Sun. Team number 8, Captain Quantum. Team number 11, D-Raptors. Team number 12, ZX. Team number 13, Alpha plus minus Alpha. And team 14, Q Disco Search. You can already stand up. Oh, and use your laptop for the presentation, actually. Yeah. If that's okay. And every other team, I'm just going to repeat them to avoid confusion, but every other team stays here. So that will be Team 1, Quantum Anti-Fraud Squad. Team 4, GBQ. GBQ. J'ai pas la ref. Ouais, ça marche. Team 5, 5 guys. Team 7, average dodo enjoyers. Team 9, no name. Team 10, no name. Team 15, quantum fire cats. And Team 16, eigen criminals. Okay. And that will be the order of passage. So I will welcome Team 1, Quantum Anti-Fraud Squad, to set up con calma. There's no rush for now. And yeah.
Vorrei anche già avere la presentazione aperta.
Stiamo aspettando che tocchi comunque.
Ok, perfetto.
Abbiamo un momento.
Ok. Forse la posso usare qua? Quindi meglio che metti qua. Appunto,
usiamo questo o... No, come no? Prova, prova.
Or if you need, just slide up to speak.
Slide up.
Yes.
Oh, for talking, slide
Yes.
up.
Just speak in front.
Devi tirare su per parlare. Okay. So, can you hear me? Yeah. Hello, everybody. We are Quantum Anti-Fraud Squad. As the name of the team says, we were tasked by Intesa San Paolo to solve a fraud detection problem with quantum machine learning algorithms. So, in this presentation, we will start by seeing the data and then apply classical methods to analyze them. Then we will move to quantum and compare the results of the two approaches. So, let's start with data. We had a highly unbalanced dataset containing 500,000 financial transactions. And how you can see in this graph, already had 10 transactions per users. We recovered 99% of our distribution. The dataset has 15 different features. Some of them are continuous, like the timestamp at which the transaction occurs in time, and others are categorical, like, for example, the ID of the bank user. We have just one column for the target, which is the fraud column. Here, the entries are binary, and 0 stands for illegal transactions, while 1 stands for a fraudulent one. The problem is that this data set is highly unbalanced. In fact, the ratio of the ones over the zeros, it's like 2%. So the ones are 2% of our total data set, so to speak. And we tried to overcome this problem with quantum computing methods, but we also applied some classical methods to see the performance and compare them. So, first of all, we did some reduction of the data. The first one, we applied PCA to reduce the features from 15 to 2. And second one, we reduce the total number of entries because, you know, we need to produce some results before the end of this hackathon, so it was quite needed. For example, here we have a population of 1,000. You can see the two reduced features and how they displace themselves in the plane for the train set and the test set. In orange, we outlined the faulty transactions, and in blue, the regular one. And as you can see from this graph, there is no trivial kernel function which can split the faulty from the legal ones. So this problem is not trivial. And as how I was saying, first of all, we applied some classical machine learning algorithms. We applied logistic regression, which squashes the results of the predictions between 0 and 1 to interpret them as probabilities. We also applied XGBoosts, which relies on tree decisions algorithm, and also a support vector machine, which tries to find the best hypersurface, which splits the true predictions from the false one. We also tried to use a time series approach for this data set, but we concluded that it was not a possible way, and so we just stopped at trying to solve this problem with a time series approach. So let's move to the quantum part. I will let you speak my teammate, Antonio.
So, related to the quantum approach, we use a variational quantum circuit, which is an hybrid model composed by a quantum evaluation and a classical optimizer. The variational quantum circuit is composed of an encoding circuit in green here and a variational part in red. And the encoding part is used to embed the data in the quantum circuit, while for the variational, is composed of rotational angle, rotational gates, and the angle parameter are optimized classically. Moving to the model developed, we use, for the encoding, we use an encoding with Rx gate and Epsilon gate, and then for the variational part is composed of a rotational gate followed by an entangling block with CNOT. And this kind of circuit is also developed by Maria Schuld in his article Circuit-Centric Quantum Classifier, and for our model we use 8 different parameter layers. And another technique developed is the reuploading technique, which it consists of re-encode the data each time a new parameter block is added. And we try the model with and without this technique.
Now we proceed analyzing the obtained results. As my colleague mentioned, we performed the test considering 10 number of epochs and using as encoding technique Rx and Ry, and with 2 features. On the y axis, we have the recall, which is the most important figure of merit for this kind of application, which is the percentage of samples correctly classified for the belonging the class of interest, that in this case is the class 1 of the fraud. And we have on the other axis the number of transactions for which we performed the test. We have that the quantum methods, the variational quantum classifier, is the purple one, and we identify the application or not of the reuploading technique with a different form of the spot. In particular, we have that the square purple spot, which corresponds to the variational quantum circuits without the reuploading technique, is the best one for what concerns the recall figure of merits, and so outperform all the other classical methods considered for comparison. Then in this slide, we can see the training time of all the considered method as function of the number of transactions. we have that the variational quantum circuits is clearly the slowest one, but in particular we have also that without reuploading technique is faster. The quantum methods is the slowest one because we choose to perform the test using a classical simulator of a quantum computer in order to evaluate the quality of the algorithm, the quality of the approach, without have issues related on non-ideal phenomena. Then we can observe the same type of trend if you notice the runtime as function of the number of transactions. And so also in this case, the variational quantum sequence is the slowest due to the classical simulation of a quantum computer, which requires a lot of matrix vector multiplication. In this slide, we try to consider together the recall, which is the most important figure of merit, and the training time, fixing the number of transactions at 10,000. We have that the variational quantum circuits without the reuploading technique, the purple square, is the best one for what concerns the performance, and so the recall, but it's clearly not really the worst one for what concerns the training time, but in general, the true quantum approach are the worst one. The really worst one is the variational quantum circuits with the reuploading technique. The same trend can be identified if you consider the runtime as function of the recall. And our work proves that quantum computing is promising for overcoming some limitation of classical machine learning, and that in particular can help in application in which the data set is strongly unbalanced, like this one. We can further improve our model with more time, clearly, changing the type of encoding and identifying the best one with the possible in the literature, and also optimizing all the hyperparameters involved in the model. And clearly, training and runtime should be reduced by exploiting the real hardware, but when the non-ideal phenomena will be reduced with a better type of quantum hardware. Thank you for your attention. We are open for questions.
Hi, thank you for the presentation. When you compare the classical models with the quantum, how do you make sure the comparison is fair? Like what size of the classical, what architecture of each classical model is the fair one to compare against a given variational quantum circuit of a specific size and ansatz?
We use the same data set, so with the PCA apply, with the same type of rescaling apply in both cases. Moreover, we consider the same operating conditions, so the same threshold for classical method and quantum method. All these things to have a more fair possible comparison between the classical and quantum method.
Yeah, he said all for me.
Okay, so the way you pre-process the data set is the
Yeah,
same?
it's the
same data set, of
And
course.
the same size, so the same number of transactions that
Yes,
is the most
yes. But what about the models? Because the models have hyperparameters, right?
The model, sorry?
The models can have hyperparameters, or not?
Yes, have hyperparameters, and the parameters that that is the same in particular is, for example, the threshold. So when we measure in the classical, using the classical method, we set the threshold to 0.1, and also for the variational quantum circuit. So in this way, it's the same. The reading is could be quite the same. So are comparable for this kind of stuff.
To have the more fair possible comparison, really.
You probably didn't have time, but I assume all these simulations with the quantum simulator was noiseless? Is that right?
Noiseless, yes.
Okay. This might be an unfair question. Do you have a sense of how it might perform with noise? Probably don't.
No, we have not tried with noise.
Because it's for evaluating the quality of the method, and having the noise can clearly decrease too much the performance for having a fair comparison with the classical method. We have noticed this type of problem.
And could you remind me how many shots you needed to, or how many shots you needed to train the
how many shots? No, we use, I don't remember, maybe 10,000 maybe.
Cool.
I have to check, but sorry for.
Maybe you said this already. What is the state of the art?
What is the state of the art?
Yes.
The state of the art, for the state of the art, for the encoding method, there are different approaches. There is the amplitude encoding, which consists of encode the data as amplitude, the amplitude. As the amplitude of the state. Sorry, I have. And we can say that for this kind of model, we developed a new type of encoding, but the RX, RY type of circuit. Why this? Because we think that this kind of encoding should can obtain good performance for this kind of classification, because adding some complexity on the model, and so for the
considering the difficulties of the data set, it's better to have a more complex
encoding, while a more easier one. And for the amplitude encoding, there are some limitation for the accuracy. Generally, I've tried this.
And last question: what do people use in the real world? That's what I mean by the state of the art. What models are used in industry for this problem?
For this kind of model, in the industry, so in TESA, they tried this kind in the classical world, or
the classical world. What is the method that they use? Yes.
Or generally, they use logistic XGBoost SVM generally. So the model that.
So it's one of the things you try.
Yes.
Yeah, more or less the best one classically is the logistic regression currently, but we outperform it with our model.
All right. Thank you.
You're welcome.
You're welcome.
Let's give them a round of applause.
Team 2. I mean, the second team here. So team 4, yeah.
Yep. Does it connect with?
Yes, with cable.
And the pointers already, or it was from them.
For them, but we can have that one. And it's not pointing. Oh, okay. Top button pointing.
Okay. And does it also pass the slides, or you have to pass on the laptop?
If you have the laptop, you can connect with the USB.
Is it okay?
Yes.
Just I take it out then, just to put it here.
Okay, perfect.
And this is mirroring the screen or extending?
Is settings from your computer.
So I have to go to display, basically, right?
Yes. Let's try.
Yeah, should
Which is the microphone, the one on the right?
That's you.
Both.
Yes, you need to speak in front of all the mic.
Why it's
Like
not?
We can try.
Like here it says that the mirror is here, but the other monitor.
Or
maybe
you can send by
maybe
email
with-
the presentation.
maybe with the adapter we do directly HDMI here. There's an HDMI here.
You can try.
It's not appearing.
You have the presentation? I can.
Yeah, it's on Slack. It's a last version on Slack.
Okay, see from there. I think we take some time.
Oh, okay.
Okay, perfect. Okay, so the pointer. Please speak always in front of you. I remember you are.
So the pointer, how does it work?
Just point first of all.
Okay.
Forward and previous.
Okay. So I should point like this, right?
Yes, you can check the changes.
Okay.
No, with the pointer, with the pointer.
Okay.
Does it change?
Yes.
Oh, cool. Okay.
But should I, so if I should stay here, I cannot really see the lights too
So
much.
you can stay here. Come here.
But the microphone doesn't work, right? Okay. No, I can just stay here and it's fine. I can point even with the arrow on the...
Yes,
Yes, perfect.
Okay. I remember that you are recording and live streaming on YouTube.
Okay, it's fine. But, can I just start when I want? I can start? Okay, nice. Okay, good morning. We are Group 4 and we worked with Generali on the analysis of systemic credit risk on ISC devices, and we implemented an approach based on QAOA and digitized counter-diabatic QAOA. So we were supervised by Matteo and mentored by Yoshi. Just as a brief outline of the problem, financial markets and institutions are nowadays highly interconnected, like in a network. So the default or the downgrade, which means the failure or the risk of failure of a company, can affect other companies. And in particular, there can be a contagion effect, just like is in a network. So it is interesting to try to estimate quantitatively this contagion effect through the market. In our case, we were concerned with a smaller subsection of the financial market that we can think about as a portfolio. So a portfolio for our interest is just a collection of companies that we can label from 1 to n, on which we invested if, for instance, we are the owners of the portfolio. So if you map each company to the vertex of a graph, then you can ask yourself the following question. Say, for instance, that company 1 fails. Does the risk propagate to company 3 with a probability that is larger than 0? If so, you draw an edge of a directed weighted graph with the weight of the edge that is proportional to the probability of contagion. So in the end of the day, the portfolio can be represented as a directed acyclic graph with weighted edges. And in particular, in this example, you can see, for instance, that the number 1 is a big company that is affecting most of the market that is interconnected with. So if company 1 fails, it is a problem for the rest of the network, while the 7 can be thought as a small startup. It is influenced by the rest of the network, but itself, if it fails, it doesn't really influence the rest of the financial market. Yeah, sure. Yes. I mean, the direction is important. So you can have an arrow pointing from 1 to 3. It means that if one fails... You also have an arrow pointing from 3 to 1 yes. In the same network. Okay, this is actually, if you write the cost function, you pay a cost for it. So it's something we don't want in the solution. So in principle, an optimal solution should not have these double arrows. You can have it, but in the cost function, if you have a term like this, you pay an energy cost. Okay, so there is a penalty for it somehow. Because it's usually not, I mean, it can be the case that both companies influence each other. It can be the case. In the Cubo formulation that I'm going to talk about shortly, which is taken from other papers, they really don't, I mean, it's possible, but they don't put a probability on that it is high. It's something like a rare, a small probability for these configurations. So in practice, in our problem, we have a data set, which is a collection of time series. We have a time series for each of the companies of the market. And in particular, these data, I mean, they are a little bit complicated and coming from the financial world. They are default credit swap. But for our interests, I mean, for our concerns, they are basically an estimate of the risk. So if you have high values of these functions, it means that you have a high risk of failure. And for instance, here you see this peak in 2020. It was due to the pandemic shock. While here, more recently, this year, there was this crisis initiated by the Silicon Valley Bank that propagated through the network. And you see that also Credit Suisse had a very high risk of default, and in the end, it actually defaulted. And the same, you see there is a correlation with the other companies. So, I mean, I don't have time to go through the details, but the idea is that you take this time series, you take snapshots of them, so a finite interval of time, and you also translate in time these snapshots so that you count for causality from one snapshot to the other. And then what you want to do is, given this data set, it's an inverse problem, you want to reconstruct the optimal graph that is describing this propagation of risk through the network. So let's say that after 2+ hours of interesting modeling and calculations, this can be mapped into Kubo problem. And in particular, you have different terms in the Hamiltonian. You have a cost function, which is just representing the cost of a graph, so you want to minimize it. And then we have some penalties. So we have one penalty that is accounted for the existence of a maximum number of parents for a node. So this means that, for instance, if you fix m equal 2, you pay an energy cost in this configuration where you have 3 parents pointing to the same node. While, yes, you also have a penalty if you have 3 cycles, because it is something you don't want to have usually. So if you have n companies and you fix this parameter m equals 2, you have a Kubo formulation with a number of binary variables that scales quadratically. And you can do the usual encoding, the base encoding in the quantum spin Z Paulis. So the name of our group is generally better if it is quantum, and we also added gate-based, because the previous work was done with quantum annealers, which have usually a limited connectivity, and you are restricted to Kubo problems. In our case, it is m equal 2. You can demonstrate if you have m larger or equal than 3, it's not a Kubo problem. It implies higher order terms in the Z Paulis. So we use a gate-based approach. And in particular, I mean, I don't have the time to go through the details of QAOA, but it is basically a hybrid classical variation algorithm where you have an ansatz that is layered. Each layer has a structure. In one case, QAOA, you have a mixer term generated by Pauli X and the problem Hamiltonian. In the other case, you have a term coming from the theory of counter-diabaticity. So the main improvements of our methods on the state of the art are that we have all-to-all connectivity. For instance, in Quantinuum devices, we performed a simulation on the emulator, and we can think about future work. And also we can go beyond Kubo, because we can implement higher order terms with the usual decomposition into gates. So I say that the number of qubits scales quadratically in the number of companies, so the number of nodes of the network, but actually there can be a dimensionality reduction that can be performed with some methods. And you see that you still have a quadratic scaling, but this is quite improved in practice. So you have the number of qubits on the y-axis, and you see that, I mean, you can perform simulation with a larger number of companies also on ISC devices. So now I will leave the floor to my friend for the results. Sure.
What's the algorithm for dimensionality?
The algorithm for dimensionality reduction was already implemented, but the idea is that if you have a matrix that is describing the correlation between companies, you put basically a threshold on the correlations, and you ignore those matrix elements that are small enough. So you kind of put a threshold, so the matrix is now sparse. Sorry?
Some kind of constraint.
Yeah, exactly. So now you have a sparse matrix, and this makes it easier. You know, you can reduce the number of qubits that you need for your encoding. I mean, to be honest, I didn't have the time to go through the details, so how you actually find this Kubo formulation is a long calculation, but if you put the constraints, the number of variables you need are less.
Yeah, so for results, basically the first thing we want to show here is the actual optimization problem, the outcome of the optimization using QAOA and DCQAOA. So we ran this problem for 1,000 steps for both 3, 4, and 5 companies. And this corresponds to 9, 10, and 15 qubits. And here we're basically showing that for each problem, we ran 20 instances of QAOA and DC QAOA. And in the graphs, we have as the dashed line is the average of these 20 instances. The shaded area is basically the standard deviation from it, and the solid colors are the best case, so the case that achieved the better result. In this case, the better result, what we want is to achieve higher values, closer to 1, because this is the normalized energy. So we divide the energy that we are finding in our circuit from the exact ground state energy. So higher is better. And as we can see here, DC QAOA outperformed by far QAOA in this case. We found using QAOA algorithms, specifically both cases for P equals 1, so for 1 layer, we found with QAOA, let's say half of the actual energy that we wanted to achieve, and DC QAOA usually converged way closer, like closer to 90 a lot %, let's say. Another interesting outcome is actually analyzing, as I said, we ran this problem for 20 instances for each case for like 3, 4, and 5 companies. So it's interesting to see the success probability for each one of these instances that the problem is ran. So basically this means how probable it is that in that instance I actually found the correct ground state. And we see that for 3 companies, 9 qubits, we basically for most of the instances, we found the ground state or have a very, very high probability of finding the ground state. And that changes a little bit when we increase the dimension of the problem and we have 4 and 5 instances, because then we go to a more sparse regime, let's say, where just in a few of the instances, I actually have a non-zero probability of finding the ground states. And specifically for 4 companies, in these cases that is non-zero, at least is still very high, like 90 a lot %. But for 5, it starts to decrease a little bit, and this ranges from 50 to 70% for the non-zero instances. So basically, we run. So you run it a lot of times, and you calculate when you find the ground state, right? So.
Yes,
what?
Exactly.
Yeah.
Yeah, it's the.
Square model.
Yeah, exactly.
Function, right?
When we solve the problem, we get a bit string because it's a classical Hamiltonian, and bit string will solve the problem. We can decode it, and this probability of finding the that bit string. Okay. Yeah. So for example, in this case, for example, it's 60%, so we get 60% probability.
Yes.
All up to the ground string. Perfect. Exactly.
Yes.
Adam optimizer. This is a simulator with Adam optimizer, yes. Why not? Yes? Sorry? Oh. No, what we actually can do on a quantum device is find the gradients using parameter shift rule. And then we can apply Adam, because once we have gradients, there is a function to evaluate with gradient. Okay? So, and parameter shift rule is much easier to do in experiments.
And that's what we've done here.
Yeah, here also we are using parameter shift rule, so also for the simulation, because we need to keep track what will happen with the real device also.
Because as I said before, we ran this problem multiple times. First in simulation, but then we also went and ran it one instance of the problem, or like one instance of the problem specifically for the case of 5 companies on the emulator, the Quantinuum emulator, the H11. And here we're showing the result that we got out of it. We're basically, in the x-axis, we have the possible bit strings that our system can, the possible states of our system, and the probability of actually that state occur in the emulation. So, and the high bar here is actually ground state. So in this run, we found that the ground state with 66 around % probability. And this graph that is being shown inside the picture is basically the representation of the network with the directed graph that Pietro explained, based on this bit string that is the output of the model. Yeah. So just to summarize and give some perspectives, we implemented a variational quantum algorithm for a financial use case, and we saw that we can improve scalability and improve quantum circuit ansatz. We did some actual experiments on Quantinuum emulator, and that can help us prove that our problem is actually implementable. And for future work, as was mentioned before, this annealing part was only possible to solve this problem for QUBO formulations, and we think that we know that with our approach, we can actually run it for beyond QUBO problems, so we can find higher correlations. And we also want to perform actual experiments, like on actual devices with Quantinuum. We wanted to run this weekend, but it was not possible. And also another interesting problem is including time dependence, so that our actually Bayesian network is not static, but yeah, varies in time, so we can analyze how that affects the approach. And yeah, that was it. Thank you.
Thank you very much. In the interest of time, I'll only take one question. Kieran, do you want to? You're good, Konstantinos?
You compared the two QAOAs against each other.
Yes.
What about classical stuff?
What about, sorry?
Classical methods.
Classical methods, with simulated annealing, classical method has already been shown complexity of NP-complete. So this problem is NP-complete, learning Bayesian networks. So we didn't go for it because we already knew kind of what complexity it is. And the other reason was we wanted to go just for NISQ devices, so we have around 20 qubits available. So we thought that it would be a better alternative to just stick to making the quantum processes better, so better than QAOA, and then just compare both the quantum methods. But yeah, so we already knew the complexity.
One thing to keep in mind is one thing is the theoretical complexity, which is worst case scenario,
yes,
principle. Mm-hmm. But here, this is in practice, and it's average case,
yep,
and finite system sizes and stuff like that. So, if you were to write a paper on this, mm-hmm, you would have to have a classical method to compare against, some baseline, yes, to see if you beat it with QAOA, and then you need a fair way to compare. Do you have an idea what would that be, if you wanted to do it?
Yeah, the classical method would be some machine learning, classical machine learning on the Bayesian network. And I mean, to be fair and honest, clearly you can take a larger system sizes with classical methods, because you see the scaling is actually pretty good, but I mean, you can do a way larger number of companies. It would be interesting for sure to benchmark our quantum methods versus the classical in the regime where we can actually perform the quantum simulations. This would be very interesting, and I think the code is also available. So we can actually do it if we go on working on that.
Nice.
And
thanks.
As a suggestion, before trying the machine learning thing, I would just try to do some energy minimization on the classical.
So basically, we can do simulated annealing because QAOA is kind of annealing based.
Yes.
So simulated annealing would be the first one.
Yeah, this would be the first step to go. Yeah.
Yeah.
Thanks.
Thank you.
Team 5 guys. Love the name, by the way. If they interrupt, I'll take into account. One of you needs to look at me. Start when you're ready, of course.
Okay.
Okay.
Yeah, let's connect.
Okay. You have the pointer. Remember to speak in front of the microphone. No, it's not a consumer. No, it's, I think we need to see the settings. Sorry, to the settings. The preference.
Sometimes I can just drag. Is it this one that is projected?
Yes, this one is projecting.
Ah, okay.
Actually, we connect one cable.
Arrange.
Arrange.
Is it supposed to display here before? Or?
No, this one. That one and the big screen.
Maybe, okay, let's put directly HDMI. Sometimes like the connectors are a bit shitty.
Okay. Okay, okay, it's taking some time. Okay.
Okay.
Okay. Speaking of the microphone, I remember you are recording and online streaming on YouTube.
Okay. Right. All right. Good morning, everyone. We are the 5 guys working on the Quandela challenge, which is all about the variational quantum eigensolver on photonic devices. So we are going to go straight into our problem statement, which is all about finding the ground state of some molecule. So suppose we are given a molecule, maybe, for example, in our case, which we took hydrogen, the hydrogen molecule and the lithium hydride molecule. We want to find the ground state of this molecule. So the problem can be modeled as in terms of the time-independent Schrödinger equation, which is given in terms of the eigenvalue problem, and our Hamiltonian, which is the electronic Hamiltonian, is given as such. So we must note that this electronic Hamiltonian is quite difficult to implement on a quantum computer. So we are going to do some steps which we are not going to outline here, which is going to put the Hamiltonian in a form which can be implemented in a quantum computer. So to continue with this, we are going to use the variational quantum eigensolver approach to find the ground state of this Hamiltonian. So what are we going to do? We are going to start with a wave function, which some given parameters. So we are going to parameterize this wave function and then use it to find the ground state of this of the Hamiltonian of our system, which we are going to be working on. So this setup here is the setup for the variational quantum eigensolver, which we are going to prepare our ground state, our wave function, which is in terms of the parameters. We are going to prepare it with some quantum gates, and we are going to, in terms of some parameters, we are going to be iteratively changing this parameter until we are going to have a better approximation of the ground state of this Hamiltonian. So to continue with our problem, I'm going to give opportunity for my group member to continue.
Okay, so to solve this problem, we use a photonic device, which is a bit different as a gate-based, like in the way we have to program it. Indeed, instead of qubits, we... Yeah.
Can you go back one slide?
What are the variables, HI, HIJ? I mean, we started with the Schrödinger equation in the continuum, like before. So you have the electrons going around ions, and now they became spins. What's the encoding?
You need to make some mapping with a Jordan-Wigner transformation in order to get to this Hamiltonian.
Okay, but Jordan-Wigner transformation works on a chain.
Yeah, but here you have I think you can encode this in terms of creation and annihilation operators for the electrons with two sides, basically, because you have... Yep.
Okay.
Fine for you? Yeah, I'm not completely sure about that, but because you have two electrons in the end for the H2, for example.
So do you discretize space in a lattice? Do you use an orbital basis? What do you do?
I'm not sure.
Not sure. Okay.
This Hamiltonian was in the description of our problem, so I guess this is the way we have to modelize it.
Okay. I don't want to take more time. Please go on.
Indeed, we're using photonic device. So the way to program a circuit in a photonic device is a bit different. We have because we don't have qubits, we have optical modes, and we can see that to create a qubit with an optical device, we can use two modes, and for instance, like the state 0 will be one photon in the first mode, 0 photon in the second mode, and state 1 will be 0 photon in first mode and 1 photon in the second mode. Also, we don't have gates, but we have two tools, like one beam splitter and a phase shifter. Both can be parameterized, so a beam splitter can rotate the state, and we can parameterize the angle, and a phase shifter can shift the phase with a parameterized phase. So to implement the circuit, we first wrote a gate-based version. So the idea is to explore all the space with 2 qubits. So we created this circuit with 7 parameters, and then we found a way to implement it with a photonic device. So instead of 2 qubits, we have 4 modes, and we use a beam splitter and some phase shifters here. And in the middle, we have a CNOT gate, which we will present in the next slide how it's implemented.
So about the CNOT gate, so of course we know that we have to translate from the qubit gates to the photonic gates. So the first way to do a CNOT gate is of course with 4 photonic channels, and this is what we've done in the classical simulation of the device. But when you go to the actual photonic device, there is because of the photonic nature, there is many mistakes that are going to happen, and you're going to have to check if the result is good, correct, or incorrect. So in order to do that, you need to add in the CNOT gate 2 additional channels that are here and this one here. And the rest of it is just the CNOT gate, how it is done with the beam splitters. Okay, and then once we know how to do those CNOT gates, we can come back to the general architecture of the process, the algorithm. So the first thing is we need to run the circuit on the photonic device. This has to be done multiple times. The reason for that is that we're going to measure the mean value of polys. And if you want to compute the mean value of the X polys or the Z polys, for example, you need to run the circuits multiple times. Once this is done, okay, so you run the circuit, and then you compute the mean energy. So in order to do this, you need to have a translation from the photonic device to the qubit basis, I mean the poly basis. And then once this is done, you just run this function many times and optimize the parameter, right, in order to minimize this energy.
Yeah, we can now show our results, and actually, like, we can see that our simulation, our expected values from the theoretical model are perfectly fit each other. So, like, we were really glad of getting this plot, because behind each one of these points there is an optimization variation quantum eigensolver that is run and has given the right answer, and it gives we see a very good accordance with the simulation. So these are simulations; these are not experiments. Then we tried to use also to run our algorithm also on a QPU by Candela, and actually, like, we can see, we tried with noise and without noise. That are two through the use of some parameters that you can set when you build up your circuit. And what we got is not really, we tried this for just one ground energy, so just one value. This is the value we were expecting, and we can see that we didn't achieve that, because, like, this represents the number of iterations and the value of energy. So we expect the energy to go down to the ground state energy, but we see that we weren't able to achieve this, probably because we didn't give enough iterations, or because the circuit implemented had some problems with the parameters, and we have been, like, studying these problems yesterday night also, but didn't find any answer. So yeah, this is what we got so far. All right.
So after doing the hydrogen atom, we want to extend to bigger molecules, so the lithium hydrogen atom. And for the lithium hydrogen, we need 4 qubits, and one of these little units of unitaries, C0 and unitaries, is a small unit. And we want to figure out where we want to put our C0 gates, so that we use minimal possible C0 gates, because the more C0s we introduce into our system, the more complicated the algorithm becomes and the more time it takes to run. And so to choose which qubits we want to put the C0 gates on, we want to compute some entanglement coefficient to see which qubits are the most entangled. And we use this formula, which is based on von Neumann entropy, to compute these coefficients to tell us how entangled any 2 qubits are. And we found that Q1 and Q2 are very entangled, Q1 and Q3, and Q2 and Q3. Yeah. Okay. So the main learnings and challenges from this project for us was learning how to scale to larger molecules, because it's more computationally expensive, and also we learned that photonics is a great technology, and also running in the cloud is quite challenging as well, because we introduce other problems. So we'll take any questions, and thank you for listening.
So, can I ask you a question? There's a question from the back.
What reference data are you using for your initial calculation? Where you started coming from?
So the input state.
Equation again, please.
How are you tapping the density matrix?
Lithium hydride.
Yeah. You say how are you calculating the density?
I think we have some code for it. So we kind of took it from one of these papers based on MI. I don't remember what MI stands for. Yeah. I'm not sure if I can answer that.
So no, we don't know which classical method we start.
And funny, you said one thing about the parameters.
Yeah, with the real simulation on QPU. Yeah, actually, like our results were not really encouraging because it was taking really long time to take each of these iteration, and like at some point it wasn't converging. Like we see that it starts oscillating, and we think that it was because there are two actual ways to implement the C0 on a quantum device. For the simulation, we used one, but for the real QPU, we used another one. And I think that that affects the parameter in some kind of way that we weren't able to figure out in time for this presentation. Actually, yeah, we can see that it doesn't converge. While if we made also the same plot for the classical for the simulation, and we saw that like actually the loss function, the energy is always like in this part of the graph. So there were some problem, I think, due to the C0 gate. Yeah. Yeah.
Testing. Okay. I was a little confused on this plot. So is one the simulator and one is the actual device? Because one says noise and one says...
No. Okay, yeah. This was like we ran two simulation on the quantum processor, and you can actually set some special parameters with the simulation on the QPU to reduce the noise or not. And so we tried them both. First, actually, mostly as a mistake because we didn't see that there were tunable parameters. So we tried with noise and without noise, and we see, yeah, that this signal is more clear than this. But yeah, this is the main difference between the two.
Okay, thanks. That clears it up.
That's going to be team 7 now, average dodo enjoyers, working on a cryptography use case. 10 minutes and they can start when, like you start whenever they start, basically. Testing. Hello. Like everyone is forward, I can't be forward. Yeah. I need to do this. I need to time.
So, where is presentation? Slideshow?
Two. So one at 5 and 8. Yeah.
How do I present?
And if they ask question, are you able to lap?
Okay, if you want to have a pointer,
then that you could use that for the question time. And
we can connect, we change the slide.
Then we keep track of everything, basically.
Okay, so I can change the slide with this?
Yes. Yeah. Forward, previous, top one for pointing. Okay, it's not mirrored the screen. We can. Okay. Yes, we need to go back because it's not mirrored on the screen.
Yes. Then I do present.
Okay. Okay, so speaking on the microphone.
Okay. Okay.
Hi everyone, thank you for being here. We are a team average Dodo enjoyers with our challenge about quantum cryptography. The presentation will follow these steps. We'll first have a brief introduction about cybersecurity, particularly in the energy sector, and then talk about the advantages of using quantum computing, and then we'll dive into the challenge with our solution. Okay, so as this data shows, the number of attacks have been steadily growing in the last years, and it is forecasted that the total amount, the total loss due to cyber criminals will reach $1 trillion by 2025. The energy sector is particularly affected by cyber criminals due to its central role to the world economy. So it is paramount for these companies to be up to date when it comes to cybersecurity. Quantum cryptography may offer an help and providing a powerful tool. Particularly, we would like to use quantum computing to generate randomness. In fact, classical way of classical random number generators are not truly random, and this may pose a vulnerability that can be exploited. On the other hand, quantum computers and quantum systems are inherently random, and so we would like to leverage this randomness for our scopes. Unfortunately, due to the sensitivity of these systems, noise may disrupt. Noise caused both by either by the environment or an adversarial attack may disrupt this randomness we want to create. Okay, I'll leave the word to my teammate.
Yeah. So now that we've seen a bit about the context, let's see what let's dive into the challenge that we had. So quantifying randomness in a noisy quantum circuit. So we provide the randomness, the random numbers with a quantum circuit that is noisy, and we try to see how this noisiness affects the randomness of the numbers. So first things first. What is it quantifying randomness? How do we do it? So we don't want just to generate something random. We actually want to be sure that it is random and how random it is. So it is important in cryptography, in quantum cryptography, to actually measure the randomness. So you're all thinking we do it with Shannon entropy. The only problem is that Shannon entropy can overestimate the randomness of what you give it. So we actually use here the minimum entropy. So you have the formula here. So it takes the worst case scenario. And so that actually interests us for cryptography because we want to know what can happen in the worst case scenario. Yes, so what can we get as a maximum random state? We want just a uniform distribution, of course. So we do that with just all Hadamard's in a circuit, since we're doing it with quantum circuits. So we were given to test the noise a toy model. So we actually had the code of the toy model, which provides noise, but we just say that it's a black box and that we tried a few circuits to see how it reacted to it. So first, if we feed it to completely the circuits are supposed to provide a uniform distribution. So for example, a whole Hadamard circuit, we can see up here what it does when it's there's no noise, and then when we apply the noise. So we see that there's a little difference though. And then we tried with a different circuit that is also supposed to provide a uniform distribution, but that is different, so the noise should maybe act differently on it. And we can sort of see that it does act differently on it, that this is actually the noisy part of this is less noisy than the first one. Yes, so we have we had the min entropy. We just didn't really put it in for some reason, but we do have these somewhere in the code.
So the previous graphs don't seem like to be. It seems like there is no difference between the results from the all Hadamard circuits and the Hadamard and C0 gate circuits affected by the noise in the previous graph. There is no differences. So, and that's is not what we expected to see. Now I will tell why we doesn't expect that. So we studied the noise model, and reading the code, we figured out how the noise model works. And all what it does is to nullify the effect of the last single qubit gate for each single qubit, and the probability of doing that is parameterized by the parameter lambda, and this is what we figured out. But so the gates that are not single qubit but are multiple qubit.
Sorry, can I ask you a question? I'm a bit confused. So,
yes,
you have at the beginning you have a circuit which just generates a random string,
yes,
uniformly distributed,
okay,
ideally, okay? So with probability 1 over 2 to the n, I get one of this. And it's enough to have Hadamard gates.
Yes, it's enough.
But then you started talking about noise.
Okay, then we apply a noise model to the circuits, and what the noise model does, after we figured out what the noise model does by studying experiments and also reading the code of the toy model.
Okay.
And have you seen that the results, the previous results from the whole Hadamard circuits with the noise? And
okay, now just a second. The C0 gates that connect the qubits to C down here. What are they? Why do you need them?
Okay, the whole Hadamard circuits and the circuit with Hadamard and C0 are two different circuits that generate a uniform distribution, but are different circuits. So we want to see how the noise model affect these two types of circuits and see the differences.
Okay, I see.
Why we this is the Hadamard and C0.
Okay, the ancillas are just to reading out the qubits.
Yes, the classical resistor.
Okay, so that symbol is just a measure.
Yes, of course.
Very good.
So,
all right. So now you have a noise model for your gates. So the gates are imperfect in some sense.
The noise model is a black box. We don't know. The noise model is implemented in order to have a noise that you don't know where the noise come from. The noise can come from the single gate measurement, the single gate itself, from the preparation of the state, from the measurement, and so the toy model is a black box that will ruins your results. Stops. So of course there is who write the code that implement the toy model want to also simulate the gate error, but it's not the only error. The toy model is a black box that will only ruins the results of our circuits independently of the type of noise. It's a black box. But so what we study the experiments and we read the code, and we figure out how this toy model works, and the effect is to nullify the last single qubit gate for each single qubit, and the probability of doing that is lambda. Okay, so when the noise is applied to all the qubits simultaneously. So you can figure out that you can avoid this noise by applying, for example, two C0 to the same qubit. That will result in identity, but then the circuit will not be affected by the noise because the toy model is this toy noise model is quite easy. An example of circuits that will not affected by this toy noise model is the G8Z state for 3 qubits, and we call this type of gates Gandalf gate because the noise will not pass from that point on the circuits. So this is Gandalf. So the C0 act as a barrier. So why our results don't show differences between the two circuits, the circuit with whole Hadamard and circuit with Hadamard and C0? It's because the vanilla implementation of the noise model have lambda equal to 0.5. And if we improve the model by changing the value of lambda, we will raise up the probability of applying the noise, and we maybe will see the a better distinguish between the first circuits and the second one. Sorry, and but what we have done is not only this, we also improved the model noise, the noise model, by adding the feature that will add a probability of applying the noise that is independent for each single qubit. Now, in the graph, that is the last thing that I will tell to you because I have to pass the yes, of course. Okay, the graph, this is a graph that will show the experimental results. The orange dots are the experimental results of the circuit with Hadamard and CNOT. Yes, so Hadamard and CNOT, but there are, we have questions, so go. Hadamard CNOT circuits with Hadamard and CNOT are the dotted circuits, the dotted line. And the red line is the results of the circuit with all the Hadamard. And you can see that the circuits with the CNOTs have a lower bound to the entropy. And that is good, no? That is good because this is useful to our task, to have a lower bound to the minimal entropy. Okay, the worst case scenario, the minimal entropy. Have a lower bound is really good. Prego.
I'll be very, very quick. So, how do we change it? Where do I have to point it? Okay. This one? No. Can I ask some help from someone?
Come on. What is it? Yeah, we're trying. Come on, what's going on? He's dying. The computer is dying.
Can you change the... because
Can you refresh? Yeah, I'm trying. It's not responding. Technical difficulties apart. Wow. Okay. Wow. Quantum computing.
my friend is taking her PC, so maybe we can look at the presentation. Even though the photo is very cute.
Remote touch.
Freccia, questo va avanti.
Freccia a destra.
Okay, now it's working. Perfect. This one. So I will be very, very quick. So what we talked about so far was the first part of the challenge. Now we go into like a theoretical point of view, and we assume that there is not a toy model. There is whatever circuit we want as a noise model. So how things change, we have to look at the worst case scenario, because in cryptography, that's everything that matters, only that. So if we have any circuit ever that implements any state, which is U, exists a lambda such that epsilon, which is the gate of the noise, undoes what U does. So what does that mean? H mean is 0, because we only have one state. And that's not good. So single circuit approach is not enough. We cannot hope to find the circuit that is perfect. what people do is take random circuits and makes this certificate protocol, which is based on the Bell's inequality. The general approach is quite difficult. We implemented it on the simpler case, which is as U, we take the GHZ state, which is HC naught, and then we take as local measurements for the first qubit, one between X and Z randomly, and for Bob, which is the second qubit, we take X or Z, but followed by a rotation on the y-axis, parameterized by theta. So what we do, we measure after that, we post-process the statistics, and we build the estimator, which is C, which is a function of the expectation values. And we have two bounds. Classical bound is 2, quantum bound is 2 square root of 2. So if we have C that is greater than 2, we are happy because we are carrying some entropy. We cannot go greater than 2 square root of 2. That's the maximum, and it carries 1 bit of entropy. So JHZ is a good state, but because it's easy to implement, but it doesn't take the maximum entropy. It only takes 1 bit of entropy, even though it's made of n qubit. So what we do, we check that Bell's inequality are violated. If they are violated, we take the measurements. So we have a string that is the output of this circuit, this device. Then we have to use a randomness extractor to search between all the string, and between the garbage find that bit of entropy which is truly random. So we will have as an output of the randomness extractor a shorter string, but that will be truly random. We use randomness extractor from quantum origin product, which is developed by Quantinuum, and I have to stress 2 things. The first is that this approach is device independent because we didn't assume anything on the noise model. The second thing is that although this second part of the challenge is theoretically motivated, we actually implemented the randomness extractor. So we actually used the package. We can take a string from the device, put into the extractor, and have a shorter string, which is random.
Okay, so super quick, I will just skip maybe this and go direct to our example. We used a case in which the inequality are fulfilled, and we see that we have 1 bit every 2 bits of information, and that's what we see. We take our random string that violates perfectly the GSH inequality, we pass it through a random noise extractor, and we get 4 bits. From a string that should have 4, but 1 every 2, we get 4 bits of random information. And that's it. That's our GitHub. We want to thank our mentor, Quantinuum, and the ICTP for providing the challenge and organizing this event, and thank you so much. Sorry for the time.
Hello. So you said in there that this is kind of a device-independent approach in the sense that you don't need to know about the noise model that the machine uses. But here you're running on a simulator, and you produce some bits that we kind of call random because you violated the bound. So, but obviously no true randomness has been generated because you ran on a simulator. So what do you think, what's wrong with that? When I say it's completely device independent, what kind of assumption do we add?
We assume that like the way that we choose the measurement, we are assuming it's completely random, but it must come from somewhere. So it's like it's not truly random in that sense. So we must take a starting key that has some, like I explained it here, like a bit there. We need to start with a starting key which has some randomness, and we assume that the key is random.
Yes.
But we don't know for sure.
But you see, you ran it on a simulator, so there's no way, there's no non-determinism in the quantum sense. So,
here?
Yeah, because we didn't run it on a real machine.
Yeah, like this is a simplified version of it. Mm-hmm. Like in this case, it's very easy to study, but in theory, we should, if we take our quantum, like GSH estimators, if they're violated, we should be able to tell that the bits we're getting out are random. This is an easy case to study because we know the rotation is only in 1 bit, so it's only one parameter to change. But if we could create a completely random circuit, we know that the CSH inequality is violated. Our bit, what we're getting out, is truly random. It's quantum.
I think essentially what I'm trying to say, you still need to assume that the thing that you're running on is still trying to implement a quantum computer. You can't just use a simulator. Like, that's the missing part of the assumption. So it's kind of what we call like a semi-device independent approach. But yes, very good.
Thank you.
I have just one comment, actually. How long was supposed the presentation?
Yeah, 10 minutes.
10 minutes. You had 15 slides. I've never seen any more than 1 slide per minute. Actually, more than 1 slide per minute.
Yeah, we thought that some slides were like super quick, but we actually didn't.
It's like 1 minute.
Yeah.
Thank you.
Next team can start preparing already.
Oh, sorry, there is a phone here.
Can the next team already set up?
the two microphone. The two.
It's connected?
It's mirrored, so you can see there and there. You have the pointer, go forward with the bottom, radius, and top pointing.
But I can go with this also.
You can do that.
Yeah, let's use this. Just forward and backward, just.
Yeah.
Okay, very good.
Okay, I remember your... Okay, I can remember that if you need. I remember you're recorded and on live streaming on YouTube. Streaming on YouTube. Thank you.
non c'è più adesso, se lo faccio perdo lo schermo oppure no? Non ho voglia di...
Aspetta, non fa niente.
Al solito
Ah, è vero. Ma no. Ah, ecco qua. Vai, a te l'onore.
That much power.
All right, presentation by Team 9, Tiki Taka Tiki Ticket, is starting now. The floor is yours.
Good morning to all. So the name of our team is Tiki Taka Tiki Ticket, and we would like to have we would like to give special thanks to Callum because he had to invest a lot with us, and also to Luca. He was not our mentor, but he helped us a lot, and so this was our first quantum experiment, or you say quantum project that we guys did. We are from MHPC team. And so the title of our presentation is Tivoli Decomposition for Grover or Oracle. So we did the Tivoli decomposition using a blog post, and then we compared with the one with Ticket, and then we had to write an oracle from scratch, and then we had to do the Grover's algorithm. So the thing that motivated us that multi-control gates, they must be compiled to single and 2-qubit gates before executing quantum algorithms on real devices, because it's difficult to implement multi-control gates in backend. So we had to decompose them using single qubits and 2-qubit system. And then there's an efficient implementation of algorithm, depends on optimizing the decomposition of multi-control gates. And so if we are not able to optimize it nicely, then we need to increase number of gates, which can lead to more noise. And So, and even the depth of the circuit increases. So the real life application that we guys also did was writing an oracle and doing the implementation in Grover's algorithm. And so we were more focused, like we had two parts. The first part was more focused on optimizing the Tifoli gates, and the second was on writing oracle and implementing on Grover's algorithm. So the task was divided into two categories. One was like optimizing the decomposition of Tifoli gates using Craig's blog post, which was suggested by Callum. And the second one was finding a nice and smart oracle to implement in Grover's algorithm. So we had to start with like doing the decomposition on using pen and paper. Then we did the classical approach using Encyclopedia bits using the same Craig's blog post. And then we did the quantum approach where we use the quantum circuit simulations as like root n, which like, and then we compared the implementation with ticket. So we proceed with our first approach. So first we did with the classical Encyclopedia approach, and then we found that like it was leading to more qubits, which was contributing more noise. So we had to go to the quantum approach, where we took the operations as root n for quantum circuits. And so what we did is breaking the n controls into sub-controls. And so the sub-controls, they have less, like the sub-process, they have less controls. And we recursively implement the function again and again, which leads to less number of gates and which leads to less noise. And so this was the result that what we could implement was, first was the one that we can see on the left, was the implementation of the blog post, where we could see that this is an intermediate step that we could implement for a 2-cubic system, and the depth of the circuit seems to be 5, and the number of gates in the circuit total used using the blog post was 5, and the NOT gates that we could find was 2. And this was an intermediate step, and after that, like this one was with the ticket, which was like decomposition with ticket. So if you have less number of qubits, then this seems to be fine. But if your gate is like you have more number of qubits, and it's like then it becomes more complicated because you have more qubits. So it's easy to decompose in the form of this approach.
Okay. So now that we have okay, can you hear me? Yeah. So now that we have optimized the gates, we would like to apply it to a real problem, and it was suggested to solve the traveling salesman problem on a quantum computer. So as you know, the traveling salesman problem, you have a bunch of cities connected in some way, and you want to visit each city once and only once. Now, what you can do is a brute force search. You can just do all paths and check if the path exists and if it is a path that visits each city once and only once. And being a brute force search, it's very amenable to put on a quantum computer using Grover's algorithm. So Grover's algorithm gives you, in a brute force search problem, like, for example, the traveling salesman problem, a quadratic speed up respect to the classical brute force search. And what you need to do for this is you have one oracle which tells you, you give it a path, and it tells you if the path is good or it's not. And then you have the amplification or the diffuser. Okay, I went too far. So the difficult part here is to build the oracle, because the diffuser is basically the same for any Grover's algorithm. And to build the oracle, you need to build, classically it's very simple. You give it a path, it checks if the path is good, and if it's good, that's it. If no, it says no. But now you need to implement this on a quantum circuit using unitary gates and doing it all by hand, only with Toffoli gates, it's a complete disaster, because how do you check that a path exists, that is good? You need to input the graph that you have for the cities. It's terrible. So what do? You just do it. And this is the circuit we get. So this is the circuit you get for, in this case, 4 cities that you want to visit. And this is just the oracle. Then you plug it into the diffuser, and you have your Grover's algorithm. If you want to do it for 5 cities, to simulate all the qubits, you need about a terabyte of RAM, so we couldn't do it. The graph? Whatever you want. Yes. So the graph impacts the circuit itself, the connectivity of the circuit. So this one is for basically a square. 4 cities and connected like this. So depending on your graph, you get a different circuit.
So, 5 cities.
Yes. Any graph. Any you want. So the number of qubits is the same for any graph. The graph itself just implements, just impacts the connections we have.
Number of qubits just depend on the vertices. The order of n squared plus n log n, the number of vertices. So you maybe can be able to do it for 5 vertices if you were able to parallelize this code. For 6, 7 vertices without implementation, it's
No. I don't know. Probably one of the last ones. But okay, anyway, so once you have this, you can... Sorry?
Do you have a slide where you show the problem?
No. So anyway, this once you have this, you can optimize it using the optimization they described before, and then plug it into the diffuser, and you have your Grover's algorithm. Maybe if you can tell him some details about.
Yeah, so basically what you want to do, as Antonello was saying, is you want to check all paths at once. So you want to take all the possible paths between, let's say, 4 vertices that pass through all the city, and first you want to put to encode this path. So the way we do it is each city corresponds to some number, and the idea was first to basically extract the number of the city from a bit representation implemented with qubit. So extract the number of the cities, and then create all the paths. So some of these paths will just not fit in the graph because some edge.
I have a problem here.
Yeah.
For me, the challenge assessment problem is the following problem. I have a graph in which the graph is fixed.
Yes.
The vertices are the cities.
Let's say something like this.
For example, something like that. So, and you can also weight with the length of the.
Okay, we just consider the equal weights.
Okay. So you want. So now you want to have.
Yes, maybe we're talking about different problems because we are not looking for a minimizer of the paths, but just of the existence of a path connecting all the cities.
So that's an Hamiltonian path.
Yes, exactly.
Okay, so
Just
the
that the
problem is not the challenge assessment. The problem is the Hamiltonian paths.
Yes. Yeah, we didn't go. We hadn't had time to go to the minimization part and putting all the weights, but that is a bit tricky. So we discussed with our mentors, and it's not that you can really minimize once you assign a weight to all of these because it's quite difficult to do on a quantum device. So what you should do is maybe put some threshold and check that we can do, and check if this graph the weight assigned to this graph is less or more than this threshold. And so you can isolate the paths which have a weight less than your threshold. But to find the actual minimum, I don't think it's possible, not in this way.
Is the Hamiltonian.
Yes, yes. But with the goal of travel. To distance. Yes, it's already something, right?
Not an easy problem.
Yes.
So we have 5 minutes of questions. A bit less, actually, 4 minutes. Yeah. Can Luca ask a question? Is that fine? Yeah.
I'd like to ask a question about when you compare the decompositions. If you go on the decomposition slide, you compare your decomposition with ticket. Can you maybe tell me a bit more what you take away from this comparison you're making here?
So this one is not the comparison, but like it's an intermediate step that we could do with that blog post, and then we have to apply the decomposition that with ticket one, because we couldn't finish this problem.
Okay, yeah. Because the problem here is that you're comparing apples with pears, right? Because the gates you're using on the left, they're more powerful than the gates you're using on the right.
Yes. So
once they have only top leads.
So these are the toffolies that we need to decompose into the other single qubit gates.
Okay, sure.
Hello. First, can we leave all questions at the end for the speakers, please? And so the intuition on the circuit, can you give me some insight there? How does that reflect the graph?
Yeah. So maybe I'm going the wrong direction. Yes. Yes. So maybe I can just sketch briefly what we are doing. So basically we have 4 sets of qubits. So as I was saying, first of all, you want to represent each city in bitwise. So basically, the number of cities is given from the beginning, so you can bound the bit you need. And basically, you just check one by one with some CNOT gates. Either this city corresponds to the number 0. If the bit string corresponds to the number 0, then you invert some of these qubits. This will correspond to the number maybe 1, and you keep doing some inversion, and basically you assign to each city the corresponding number in decimal notations, let's say. Yeah, so basically you have some qubits, some set of qubits representing all the cities, and to each of these you will have as many ancilla as the number of the cities, and with these... Sorry? Sorry, can you hear? Yeah, I mean, I can be very precise with the number of qubits. It's something like n squared plus n log n plus some constant. So basically, in this way, you will shoot just one of the ancilla, which will be the one corresponding to the exact number of the city for each city. In this way, you can identify basically which number you are looking at. So of all these ancilla, just one of these will be shot and will be the identifier for the number of the city. So this is just for encoding one path. Then the first thing you want to check is that this path is Hamiltonian, so that passes through every city. So what you want to ask is that for the ancilla number as 0, 1, etc., for all the ancilla number as 0, there's exactly one that has been shot. That exactly one that has been shot for the ancilla number as 1. So you can do it with a CNOT gate as well, and save the result in some auxiliary ancilla. So you will need another n of qubits. So at this point, you just isolated all the Hamiltonian paths from your bit strings, but now you want to check that they can actually fit your graph. And this you can do just looking at the adjacency matrix. So the adjacency matrix is your input. This is just classical, just a small matrix. And basically, you check for okay, for example, this one, maybe something like this. Am I going out of line? Maybe I am. Basically, you check all the edges that are present in the path, and you try to connect the two cities with the edge. And so this will isolate all the paths that can fit in the graph. And basically, these you will need some other edges some other ancilla qubit that correspond to the edges. So now, one side you've checked that the path is Hamiltonian. On the other side, you've checked that the path actually fits in the graph. And then you just put a CNOT gate between these two checks, and you actually get if the path exists or not. Yes, a lot of CNOTs, yes, which are then solved by the girls team.
Okay, one but very quick question and very quick answer, please.
Just a yes or no?
No.
Did you actually beat Greg Gidney's brain or not?
Sorry again?
Did you compile better than Greg Gidney or not?
So we compiled the circuit on PTEC, on Ticket, and it works. I mean,
Better than Greg's...
Better than? No, we didn't check that. Great.
The answer is
paper you referred. No, we haven't tried to check that. No. I mean, we haven't checked the path, the timing versus the paper of Greg.
So it's not completely matched to each other, so we don't use in this part and we use this here.
Okay, all good. Thank you very much. Next team, Team 10.
It's here.
Okay.
But there is no full screen. It's not showing the. Wait, move. Okay. Okay.
Like this. Don't speak too fast. Tell me, you want me to give you a reminder, like 5 minutes?
Yeah, 5 minutes. Oh, at 5 and 8, I guess.
5 and 8 we could do.
5 and 8?
Yes.
Perfect, I'll do that. So one of you, look at me. Wave. Take that into account, don't worry.
Test.
Sure. I probably use laptops on here. I use this for pointing, right? Yes. This, the top one. So, hello everyone, we are Team 10 and we are team
call for Krylov if you're into Call of Duty, and we worked on quantum Krylov methods to find out energies of molecules. And we were mentored by Nathan Fitzpatrick from Quantinuum. So since we're working with finding the energies of molecules, we will need a Hamiltonian to begin. So we used our Hamiltonian for hydrogen molecule, and we had second quantized harmonic Hamiltonian, and then we used in quanta from Quantinuum to convert it to our weighted combination of Pauli's, that is basically the qubit encoding. So we will also need a reference state. For us, it's a simple reference state of 1100 ket that we get from the circuit of two simple NOT gates. Then, so this is our quantum subspace Krylov method, right? So as you can see, basically it's a hybrid algorithm where you use the classical portion here to calculate the eigenvalue problem, and we use to populate the matrices from F and A, so the H matrix and S matrix using the quantum computer. So basically, as you see from the equations here, and eigenvector here, it's the eigenvector for the usual standard problem is 2n into 1, right? And for a quantum subspace, you divide it into subspace, so you have a much smaller subspace of m into 1. So here m is significantly lower than 2n, right? So you already can guess the advantage here. So, and also for the novelty of our approach, we are the method we're implementing are quite new. It's both of the papers in 2022 and it's 2023, so you can see there aren't too many references or tutorials lying around for us to play with, so it's quite novel. So basically, as you can see, finding the energies is a generalized eigenvalue problem that we solve for HC equals to ESC, where H is the Hamiltonian, C is the eigenvector, and S being the overlap matrix. Then from E, we get the energies of the molecules we are looking for. So these scales is combinatorial scaling, but Krylov methods are found around this scaling. So for the Krylov subspace method, we have two inputs of H and S, and we get the output of E and C, where we use the E for finding the eigenvalues, right? So Krylov method is basically a weighted linear combination of the powers of function of H applied to our reference state, that is psi not ket, right? Then if you see, we use that powers of function of H and use it for time evolution. So we need both real time evolution and imaginary time evolution. So as you can see, for the standard Krylov, we measure expectation values of both H Hamiltonian matrix and the overlap matrix. And the difference between the two matrices are basically in H you have the Hamiltonian, and S you don't have the Hamiltonian. Yes. Yeah, we generate a subspace, yeah. Yeah, that's for the unitary Krylov method. We will be getting that to our next slides. It's included in our slides. So we are talking about standard Krylov method, and the unitary Krylov method is for the quantum computers. Yeah.
So, I mean,
yeah.
What you're saying is you have again classical Krylov method. F of H is polynomial,
yes.
low order, H squared,
So for yeah, the exponential works better on quantum computer.
We will get we will get to unitary Krylov in the next slide.
So you apply unitary Krylov methods for quantum computers, but standards is for classical solvers. Okay. Yeah. So as we can see, the complexity shifts to matrix element calculations. So that's our whole difficulty. And from the previous slide, the M and N are the indices of the elements of the matrices. So we are calculating the matrix elements. And so the indices are the powers of our, the function of our H, right? And you can see here, this is the unitary Krylov which we implement on the quantum computer. And as we can see, it significantly reduces the number of elements compared to the standard Krylov, as we can see in the next slide. We also use this array view, so it helps us to like visualize what's happening and also the dimensions of the operators that we're using. And we can see that since we are exponentiating the Hamiltonian, the number of elements are lower And that's what we wanted to show with this array view, a pictorial, intuitive view to see the advantage. And this is the overlap matrix S, and you can also see the, how the dimensions there are. And as I mentioned before, there is no Hamiltonian in the S matrix. And we now also see how the Krylov basis actually is portrayed pictorially with the evolution operators, that is the functions of h to the power on the reference state psi naught, and then we get psi 1, psi 2, and we add them up, so it's linear, weighted linear combinations of the Krylov basis, psi naught, psi 1, psi 2, right? And you can see how those operates and how the boxes of the time evolution scales with the powers. And we get the powers from the indices of the matrix, right? So as we said, it's a time evolution operator, right? So we need both real and imaginary time evolution operator. And for our case, we use totalization method. So for totalization method, you basically get slices of the time and you operate them consecutively on one after another. And to get the trotter steps, each of the trotter step we get from our Hamiltonian itself. So you have H alpha, P alpha summation, right? So for each H alpha, P alpha, you get one time slice. And you apply them on. So you actually get the time slices depends on the number of terms in the Hamiltonian, the Pauli matrices, right? So,
and so to calculate the expected values, which is the Hadamard test, and this is important because we can get the real and the imaginary Hadamard values depending on the phase gate W we have here. So for imaginary expectation value, we apply an S phase, and for the real expectation value, we don't apply a phase gate at all. Here is just how we get the counts, and you can see that that we can get the elements by applying these equations that should get us the real and imaginary expected values, and when we add them up together with a phase factor, that we get the result that we want. So this is for the simulator, and for exponent shading, which I think is kind of the most important part of the project, we use a Pauli gadget. So this circuit implements an exponential function that has a Pauli string in its parameter. So this is the circuit primitive, and you can see how we use basis changes depending on the gates that we have in our Pauli string. And this is the one that we made in Ticket. So in Ticket, there's a function called polyexp polyxbox that allows you to do this circuit, but we made our own routine. So this circuit we made ourselves, and this is just one case for a specific Pauli string. Since we have a linear combination of Pauli strings, of exponential Pauli strings, sorry, we have to make a Pauli gadget for each one and then append them. And you can see that our Pauli gadget is equivalent to using the Pauli exponential box, which you would use in quantum with a quantum control box, which would be used for a control unitary in the Hadamard test circuit. But the top 3 steps can be done by Ticket, but our approach is more it's significantly simpler because we just made the circuit specific for our problem. You can see how for a Krylov's depth 3, for the Ket 3 or Ket 2, for example, we just apply the circuit 3 times. So this is just for easy visualization. We also compiled it using Ticket's inbuilt circuit compiler to remove some redundancies that might arise in the circuit. And you can see how we had the Hadamard tests here in order to perform the Hadamard test. So for trotterization, we this is what I explained previously. There's quite a difference between our circuit, and this is due to the indices being from top to bottom. So we start at 0 at top and then at the bottom, and these indices start from 0 at the bottom, and it just flips the circuit. But you can see how the scaling of this is kind of a bit harder to do. The scaling has nothing to do with Krylov, it's more with the trotterization algorithm. So if there's with the phase estimation algorithm. So the number of Tubi gates, it corresponds to 2n plus 1 where n is the number of Pauli terms in one element of the qubit Hamiltonian. It's the number of the Pauli string. This is just the worst case because there are Hamiltonians, there are terms in the Hamiltonian that don't include all the qubits for the Pauli string. So for example, in this one, we have 3 Pauli matrices, or well, in this one we have 4, but this is just one case where it's, every Pauli gate is used. Okay, so to compare our results, we used exact diagonalization, and since this was a sparse matrix, it was a kind of a very useful thing to do, and not really costly to simulate. But this is not really the point. This is just a comparison for the eigenstate and the various excited states of H2 molecule. We did a SciPy approximation. I will talk about some of the problems with that we arose here, but basically we tried to use SciPy to do the exponentiation of the matrices. This is how fast they converged. So depending on the classical trotter length, we have you can see how the interatomic distance varies. This is the derivative plot for the eigenstate. So each point here is the final eigenstate that it has converged to, and you can see how fast it tries to converge using SciPy. Again, this is just for simulation. We also used a variational quantum eigensolver in order to try to approximate a better state than our 1100 ansatz. We ran it in Quanto backend and noisy in Quanto backend as well. However, for the summary, we see that we have here the exact eigenvalues, and now for using 1100 as an ansatz, using SciPy, we got one excited state for free. We had some problems with the dependence of the H matrices. So there were some sort of issues that arose that the matrices were not really Hermitian, and that depends on the subspace. Okay, I will wrap it up. Sorry, this supposed to be a -1. We didn't really get a correct result using quantum simulation. We think it's because of the trotter code that they didn't really implement correctly, but this is more of a, I explained it here. It's more of a future step, so we could fix the trotter and aim to get the comparable results to SciPy and the traditional VQE results. And you can see that this is the qubit Hamiltonian that we originally get. And we tried to get like a section using Krylov method, but it kind of failed in the quantum implementation and in the SciPy implementation as well. This has something to do with the Krylov space symmetries and that the symmetry preserving nature of the imaginary and real time evolution operators. These were the references that we used, and we would like to really thank our mentor, Nathan Fitzpatrick, and ICTP and Quantinuum. So yes, if you have any questions.
Thank you very much. Priority to the jury for questions, and if they have none, then the public can also take some. 2 minutes for questions.
We can go back to the question you asked before, or I'm sorry, could you repeat? I couldn't get it before.
Oh, I don't remember it.
It was something about the function with the exponentiation, right?
Yeah. So I was talking about exactly, but then you diverted a lot from there, so I'm not sure that's an issue anymore. So in some sense, on a classical computer, you don't do the Krylov method with f of h, which is more than a low-order polynomial, because simply that is, so you apply h on a vector, and the gain is in the fact that when you apply h to a vector, you get a vector which is not, it does not, it's in a particular subspace. Okay. And if you take I powers of h, and this is due to the fact that h is sparse, so typical physical h's are sparse because there is locality, because of everything. I mean, it's difficult to have an h which is fully connected in real physics examples. Which is a dense matrix. Okay, I was thinking about a graph. But what you're doing here with Krylov on a quantum computer is more like phase estimation in some sense.
Yes,
you're using the fact that e to the minus IHT on a quantum computer is a natural thing.
Yeah, it's like we have to propagate the thing, and the use of unitary Krylov is that we don't have to do this matrix multiplication as with standard Krylov.
Exactly.
So we can just put it inside the exponential, the phase and those terms.
So for a quantum computer, probably h to the fourth will be also a difficult thing to do.
Yes,
some of the... easy, it's either h or e to the minus IHT.
I think some of our references in here like outline H4 and H6, and they do outline that it becomes somewhat difficult for the quantum computer. But the main, I think the main like future work could be done into a phase estimation algorithm instead of using the Krylov method. The Krylov method offers, like we found out that it offers a significant advantage in combining the classical and quantum approach because you have a smaller basis, you have a smaller matrix to diagonalize. But yes, you can see it's very new research, but we hope to continue on with the project. We liked it. We like it very much.
Okay.
I have maybe just a brief question. You mentioned that you used a ticket. I'm not necessarily I'm not a ticket person, so I'm not necessarily fishing for endorsement. But I was just curious, how much did that? Do you know how much that helped optimize the circuit?
We tried.
Quick
question. We couldn't really get some quantum, like the matrices you see here are not, like they're so dependent that we couldn't get an estimate for the quantum approach. But we tried using compilers and not compiling the gates, and we couldn't really find an advantage. Like it did so fast, the optimization, that we didn't really find an advantage in the computation time per se. But for the results, we cannot say if it compiled correctly or if it didn't compile correctly, because we didn't get good results that approximated the SciPy simulation. So. Yes, it's hand coded, so. Yeah, PyTicket did compile some of the things, but the circuits became so large that we just couldn't really even include them in the presentation.
Good, thank you very much.
Thank you.
Now, Team 15, Quantum Firecats.
Okay, so you have the pointer, the bottom point. You're the speaker?
Yes.
Okay. Okay, you need to change the slide with the arrow key. Okay. Remember, you are recorded and on live stream.
Okay. Okay, good morning, everyone. I hope don't be so tired right now. Okay, we are the Team 15, and we are Quantum Firecats. Our project consists in quantum error correction, and our mentor was Dr. Ben Krieger. Okay, sorry. Our motivation, only in quantum computing, we have a lot of errors, right? So all the community put too much effort to trying to fix these errors or compensate these errors. If we remember in the slices of error, we say the quantum computing have one error, an average, one error per 10 to the 3 operations. So this is a huge error because we made a lot of computation. So that is the motivation of this project. And as well, we increase the confiability. If we put too much effort in this quantum error correction, we increase the confiability of the results of these algorithms. Okay, our main task was the implementation of the optimal and efficient decoding of concatenated quantum blocks using Python, and this is the QR code is the reference of we take it for implement these quantum corrections. Okay, our main goal as well is to reproduce the following results that we found in this reference. Or the description of our system is we have 5 qubits and with different levels of concatenations. We explain later what mean concatenations. And using a Monte Carlo sampling to generate these errors. And after that, with different depolarization rates. And we try to get the same results for probability of erroneous decoding. So with these tools, we try to fix our problems, the main problems in quantum computing. And as spoiler, we replicate this data. Okay, this plot will explain a little bit later. Okay, so
thank you, Alfredo. So imagine that we want to apply this our implementation of the most efficient and the optimal implementation of a decoder to solve the issue of having a noise, having a message that is subject to noise. Imagine that Alice wants to talk with Bob. So Alice will send a message that is a quantum state, and then the message passes to the encoder. Then it will be subject to a noise, and then the decoder helps Bob to get the message. But we don't know if Bob will get the proper message or not. So the correct information. We will understand because we know that the Pauli operator will act on the quantum message. And if the Pauli operator will be the matrix, the identity matrix, then Bob will be able to get the message. Otherwise, he will get the wrong message. And given a certain set of pure error, stabilizer, and logical Pauli operator, then we develop the algorithm, the ones as should be the most efficient at the optimal realization of a decoder of a different layer. Now, I let you, Irina, to explain.
Okay, so sorry, this is going to be a little bit technical because we're programmers, we have to talk about details. So when we have concatenation algorithm, the idea is that we take the system and we encode it in a bigger system, and like this we can reduce the error. So each level in the tree reproduce the encoding level. Here, this is a tree with only like 3 nodes because well, it's impossible to draw 5 on the picture. It looks way too crowded. So just imagine that you see 5. So we did it on the 5 qubits. That's why it's 5. And okay. So the idea is that we work on 5 qubits. So we put them through that function that we didn't write on the slides because it's too complicated. No one's going to pay attention anyway. It's in the article. So we work with our 5 qubits, and then we pass the information to the next level. Basically, this concatenation
that the article was discussed was using this message passing algorithm, meaning that what we pass is the state that, that we calculated, like knowing the initial error for the simulator, and we pass the probabilities that the decoder guessed, basically. And when you ask this question, what's the difference between like the straight line and the dash there? So here, one of them was when you pass all the probabilities at each level, and then you use them in the next algorithm. And the other was that you take like the maximum of them, and you only set that to 1, and then the rest is 0. So it becomes a different algorithm, a little bit different, and it scales worse, and so it's better to pass the probabilities. So that was what we were implementing with passing the probabilities. Now, when you look at this tree, so, well, power of 5, you can imagine how fast this grows. There is no way you can store this thing in memory. So we had to design like the way to go around the tree, but not store this. So basically, as I showed, we started with just this. We pass one message to the next level. Then we go here, we pass one more message. You see now we have like 2 things at the next level. And basically in this algorithm, we never have to store any more than just the number of qubits per level of the information. So even though this is exponentially many things, you don't need terabytes of memory. You only need just one matrix to store those 5 per level. So you just go around. Once you got 5 at this level, you pass it further, and then you just continue. You go down and you continue passing like this. At the end, you have some result. So you have this state that you calculated from your like initial error things, and you have what the decoder guessed, the probability. So basically, you can compare them. You can say, did it work, didn't work, or like did not work. So then, what you do to estimate how this actually works? So you do the Monte Carlo simulation.
Yeah, so in one run, we introduce an error, we know what is the error, and then we compare if our decoder is able to find this error or not. And then we do this many times, this is the Monte Carlo part, and we count how many misses we had, how many times the decoder was not able to find the errors, and we estimated the probability of error. It's the graph that we reproduced that we were able to do as in the reference. So in the first column we have, for 0, we have the physical error, and then here are the levels of concatenation. What is the best result? The best result is that my decoder finds all errors, so we have a probability of error 0. And this is able, we can see we are able to achieve this till certain levels. If the level of error is greater than this, the algorithm is not able to do.
We also timed our algorithm for different concatenation levels, and we observed that it increases exponentially, and this is what we expect because with each concatenation level, the data we are dealing with increases exponentially as well. So let's go on to the last 2 slides. So in conclusion, we observed that our algorithm scales linearly with the number of qubits as we expect, and it varies exponentially with the number of layers as expected again. So it's good. We were able to reproduce the exact same results that we were supposed to reproduce, and we are successfully getting the exact scaling behavior that we wanted to get. So let's move on to the new things that we added in our implementation. First is we implemented our tree algorithm, and this algorithm has never been done in this way, so we are the first ones to implement the tree algorithm. the major advantage for tree algorithm is that you don't have to deal with terabytes of data in one time, but you can take just 5 blocks of memory. And people usually you do this in different ways, but we did it by implementing a tree. And secondly, this is the first and also this tree can also be used in other applications, not just this application. So other industrial applications can use this tree. Secondly, this is the first and the only Python code which does this. So we can even make a module out of this after cleaning it up a bit and optimizing it. Thirdly, since all of us come from a HPC background, we believe that this code can be optimized so much better because we just had 2 days, so we just wrote it in Python, and we could do it in C or C++ because Python has nasty way of memory allocation. So, and implementing a tree in Python is worse. So I feel our estimate is that it will at least be 20 times faster if we do it on C or C++. And with this, we would like to thank all the organizers, jury, and all of you. Thank you.
Thank you very much. We have very good timekeeping, by the way. We have 5 minutes for questions.
I was curious about the noise model. How did you introduce the noise? Was it like the code capacity or the circuit level, or I don't know if you know those terminologies, but yeah, could you explain more about the noise model?
Right, about saying, I don't know if we know this terminology because, yeah, we are not really specialists in quantum computing.
Sure.
So we were given, an algorithm that has some God-given input. So noise is somewhere there in this God-given input. And then we get, stabilizers for this 5 qubits. We worked on 5 qubits, but this algorithm can be implemented on whatever. So someone who is a quantum computer scientist should give us, how many qubits, what they come from, whatever history it is. And then we encode these, in stabilizers and all the pure error, whatever other things there are, and run the code. So I cannot really answer about the noise because this is a question for quantum computing scientists.
But we use a random uniform generator with that probability of 0.1, 0.15.
Yeah, this.
So you have some qubits, you apply some noise to it, and then you measure the operators, the parity checks, and from those.
It's this is just for error correction. So you have these qubits, and then you introduce the error randomly, basically.
Yeah.
That's the thing.
Have some.
You have the initial, you have the probability of this qubit to be like an error, and then this error just propagates with things.
And you just okay. Do you know what sort of simulator you used to calculate these things?
Yeah, so simulators. I mean, the tree goes together with a simulator that gets this error thing, and it knows more what it should be because you just multiply Pauli matrices, right? So at the end you get what your simulator has and what your error decoder guessed at the same time. So both the decoder and the simulator, they're inside this tree.
Okay. Okay, cool. Thank you.
So you find that your stabilizer, your error correction has a threshold.
Yes.
Did you develop, you didn't do a systematic study, but did you develop an intuition how this threshold should go with the number of qubits?
Well, probably not really, because you need, to really implement this as a real task and play with number of qubits. Then, instead of 5, you take 6 or whatever. It's a good master thesis for us. It will take a lot of time to implement, not in one day. So that's why I wouldn't say I have an intuition. There's something will change, sure. But
and we also discussed this exact same thing with our supervisor, and he said that just do this and
because there's no time.
Oh, I understand, but I was wondering whether you developed an intuition. Okay, this looks like a percolation problem in some sense on the tree. So maybe, you know, if you thought, also the threshold is like 1.18, which is more or less 1/5.
This is probably a good question for Ben, who works on this.
Good. Thank you very much. And now, last but not least, eigencriminals.
You guys can try to use this. Three of us.
All three of us.
Yes. Yeah.
2 minutes, probably. 2 minutes. Yeah, I think 2 minutes should do. Yeah. Got it. Okay. Thank you. What the heck just happened? Something just happened.
Okay, connected? Okay.
Okay. I don't know where we just went, but I lost everything. Oh, here it is. Okay. There we go. Hold up. That's it.
I can see that. You like F11 or something?
Extend desktop. Let's do that.
No.
Hold up. It's giving me the spinning wheel of death. I will shortly move this over. There.
Okay. It's already very big on the screen, so I don't think
yeah,
we need to go really full screen.
Sorry, I did something. I'll have to adjust this and that every time we switch
Push this.
sides. Awesome. Thank you.
Yeah. So can you try it on the presenter?
It's better to present like normally. Like from here. It's better to just use the clicker for this.
Yeah. Okay.
I can take the card if you want. Okay. Can you
so
test the clicker? Is it just the side buttons?
You need to connect to the USB key. Okay.
That's okay. We can just use the arrows.
For pointing to the top.
Okay.
This is for pointing.
There we go.
Here, please speak on the microphone. Remember to have recorded and live streaming on.
Awesome. Thank you. Testing.
Yes.
Awesome. I'm starting in the Oh, yeah. All right, hello, everybody. My name is Saket. This is Kevin and Bao. We are the Eigencriminals. And I know you guys have heard quite a few machine learning presentations today. I know there was some VQE, some QAOA, all that good stuff. I'm here to tell you we're not doing any of that. We are doing filtering VQE. Sorry. But yeah, before we start, just wanted to give a huge thank you to Gabriel for guiding us through this, teaching us the basics of FVQE, and allowing us to explore and make our own mistakes and discoveries. Yeah, so first of all, before we talk about what our process with VQE, we talk about what exactly FVQE is. So the problem is that we have a probabilistic distribution of the Hamiltonians of a system, and we want to reach the ground state with a high probability. So as you can see, we perform, in theory, a transform that takes us from a low probability of the ground state to a high probability of the ground state. But we call this transform a filter. But for a quantum machine, since it's not directly always possible to apply the exact filter on the system, we use a quantum variational algorithm to incrementally modify the landscape of the algorithm. In doing so, we use a cost function. By building a cost function, we can optimize the amount by which our ground state probability tends towards the maximum at each step. And yeah, now for our approach to the project. To begin building the cost function, we started by solving the weighted max cut problem. Here we go. There we go. We started by solving the weighted max cut problem. We took the cost function of the problem, integrated it into the FVQE using a software called QJAX, which is good for gradients. And we developed Ansatz for our circuit, so we could initialize our circuit before we implemented FVQE, after which we implemented parameter shift, both the theoretical exact parameter shift and an estimation via circuit sampling. After that, we kind of explored FVQE. We looked at the different ansatz and problem sizes and how well they scale. We looked at various filtering functions to see if we could compose multiple filtering functions together to create a better one. We also looked at multiple hyperparameters such as tau, which is a hyperparameter in the filtering function, and the learning rate of the VQE itself. And we also capped us off by comparing our solution between a noiseless system and a noisy system. So we tested multiple backends as well. Yeah, so we started with in essence. Well, we use the variational quantum algorithm that gives us a stepwise simulation of this transform, and step by step we apply gradient descent and see how well that maps over to this transform, and incrementally over multiple steps it simulates something as close as we can approximate to the transform we're looking for. So the filter inherently is a function, right? But the function, what we use is we build that function into the variation algorithm so that we kind of give it a stepwise growth. How do we apply a function which is not unitary? You could do a better job explaining that.
Go into the first slide.
The first slide.
That's one. So that's probably what we're doing.
You want to go ahead and explain it? I think I'm not communicating it as well.
So this function is unitary?
Yes. So the f function shown in this map is unitary. The filtering function overall may not necessarily be unitary, but we break it down.
How do you implement it on a function?
Yeah, we don't implement the exact function. We implement an approximation within the VQE. We use the cost function to kind of map it out in a similar manner. Yeah. That approximates the filtering function, yeah. That's right. Okay. Sorry. Yeah. So we started off by solving the max cut problem. We chose the max cut problem because it's a simple combinatorial optimization problem, and therefore it has a very simple cost function to calculate. In theory, this is just a black box because in order to initialize the FVQE, we just need some sort of black box function that maps us from x to a function of x. So we used the max cut cost function as a black box with which we'd apply the filtering VQE. We made a graph with weights. We applied the cost function. We solved for the optimal solutions. And we took all the optimal solutions, scaled them between 0 and 1, and created a Hamiltonian, in a sense, from that. And the lowest entry on that was treated as the ground state, which we were trying to optimize the probability for, or maximize the probability for. After that, we moved over to creating the FVQE circuit itself, which started off with the ansatz. For this, I will hand this off to Kevin.
Okay. Well, it turns out that actually we need the ansatz for this to implement the FVQE. So in order to do that, we choose these three ansatz that was not selected randomly. We actually based on this paper because these three particular ansatz have different levels of expressibility in which we can compare or use like some sort of evaluation in the performance of the FVQE. Okay, so let's move on to, how can I change that? Okay, so this is the result for the first part of the ansatz. So as you can see here, we actually implemented for a few number of qubits, just 3, 5, 7, 9, and 11, and 13. And as you can see, actually, in all of these cases, successfully converge, and we just like have a decreasing of the rate, of the conversion rate, in order as we increase the number of qubits. So this is something that actually we take care in the following implementation. Also, one thing that I want to point out, and in the next slide I will do it again, is this kind of fluctuation at the end of the probability of the ground state that as soon as they arrive, well, this can be modified just changing the learning rate. Okay, so this is already resolved for the other two ansatz, the first one and the other two, and I want to see here that I want to show here that actually for the second ansatz, that was the ansatz that has more expressibility, they has a better, in this case, convergence rate because it has more parameters, so and more expressibility, so we can tend to reach the ground state probability much faster. Okay, so what happens when we do this kind of circuits a little bit more bigger? So here you can see that using 19 qubits, we are simulating the ansatz 1, 2, and 3 with different kind of layer, and also I think that you can see here the number of parameters that each ansatz require for given a number of layers. So it turns out that actually for the case of the ansatz 2, that is, well, it has like 418 parameters, so we just simulate, in this case, just one layer because it has a lot of time required to implement this kind of things. Okay, so as you can see here, actually we don't have any kind of problem in case if we increase the number of qubits, but it takes a little bit more of time. So let's move on here. So let me see. So what about the filter? So in this case, I will return this stage to Saket. So.
Well, it's not filtering VQE unless we have filters. So what about the filters, right? The most commonly used filters were the inverse, exponential, and cosine filter functions. So those were the ones we tried simulating with the cost function. The inverse easily outperformed the other two. We decided to experiment a little bit more and wondered what would happen if we tried composing a filtering function that stacked multiple of these. So for example, as you can see in the graph here, The orange line here is a composition of the inverse and the cosine filter functions, and the green line here is a composition of the inverse and the exponential filter functions. As we can see, compared to all of these, just the simple inverse function was the most efficient to map towards, as it not only converged to a high probability the fastest, but it was the only one that lasted for more than 7 qubits. Afterwards, all of the other composition functions tended towards a 0 probability for the ground state. After we finished comparing the filters, we moved on to hyperparameter comparisons. The first we tested was the tau hyperparameter that was in the filtering functions. We tested this for a range of values from 0.01 to 5. Our conclusion was pretty straightforward. It showed that a high tau would lead to a faster growth in the curve, and therefore it would reach a high probability faster. But at the same time, no matter what value of tau we used, for the most part, the system was pretty robust in handling the change. We also tried with variable taus. So we built this in such a way that the tau would adjust, in a sense, as the probabilities changed. It would be we built it as an adjustment function of the cost function. And even with that, up to 19 qubits, we saw no difference at all in the growth of the curves. After we checked the tau, we also checked out the learning rates. Unlike the tau, we saw a great deal of difference with these. For consistent learning rates, we tested from 0.1 through 1. As you can see over here, the lower learning rates didn't converge quickly enough. About 0.35 was a very good convergence. Anything over that, the system would overcorrect itself and fluctuate a lot as it got near a high probability rate. In theory, the highest rate possible would be pi over 2. Anything beyond that would converge pretty much immediately to a 0 probability. But we were able to figure out a way to stabilize up top by creating an adaptive learning rate that was a function of the cost function and the learning rate itself. So we realized that this works really well. The optimal learning rate that worked for this was a 0.9 learning rate. After this, we tested on noisy and noiseless systems for, we used the IBM Q Hanoi noisy backend to simulate. We did noisy simulations for 3 qubits, 5 qubits, 7 qubits, 9 qubits, and 11 qubits. For the ansatz that worked the best earlier on, since it was too big for multiple qubits on a noisy backend, we only tested for 3 and 5 qubits. The rest we used ansatz 1 and 3. As we can see, as the qubit size, as the number of qubits increases, the adaptive learning rate did function the best out of everything. And I think that's the conclusion is we were able to build a simulation of the filtering functions using FVQE. Creating an adaptive learning rate gave us a very good convergence towards a high probability, whereas other variables were a little bit less rewarding. Thank you.
Okay, thank you very much. That leaves us, let's say, okay, 2 minutes for questions.
Hi. Can we go back to how the filter is applied? This was a classical problem. The Hamiltonian is diagonal, right?
Yes.
Could you apply this filter technique to a quantum Hamiltonian?
To a quantum Hamiltonian?
Yeah.
In theory, I don't see why not. In practice, we haven't tested it out yet. That's actually something we were...
It's an in theory question.
Right.
Is there any obstruction? Because the filter, can the way in which you apply the filter be generalized to Hamiltonians that are generic and non-diagonal, like chemistry, whatever?
Maybe if you explain how do you apply the filter.
So yeah, we applied the filter just by using the filter was applied over the values of the eigenstates themselves. So even in a more quantum, like a proper quantum Hamiltonian, like as long as we're optimizing just for increasing the probability of the ground state, which is the lowest eigenstate, it's definitely possible to apply filters and do that.
Which is the whole point of quantum Hamiltonians. So for classical Hamiltonians, maybe it's much easier to apply these filters.
Perhaps. Yeah. So obviously what we did here is the cost function we used was from the max cut problem, which is a classical computing problem. So the data sets we generated as a result of that.
Right, and this is why you can apply your classical function directly in the cost function. Because you know the energies.
Right.
And you know what the eigenstates are.
Right.
And you are applying it on the energies directly.
Right.
Right?
Right.
Okay. I see. That clears stuff up there. Thanks.
Thank you very much. And that closes the hackathon, I think. I think upstairs there. Yeah. Sure, I mean, I'm pretty sure not everyone is here, but one piece of info at least to start with. There's no lunch here, as was said this morning. The lunch will be at the cocktail place. The shuttles start at 1:15 for the first shuttle and 1:45 for the second one, departing from here. Yeah, so you've got time to chill and to starve for a bit.